Okay, I'm getting Stonewall Pass on the attack radar now.
Good. What's the range?
26 miles.
Okay. Inertial computer checks with that. Let's look at it in situation for a minute when we're 5 miles out.
These smaller hills just ahead are painting all right. Let's keep the E-scope till we get a pull-up for Toluca Peak.
Okay. I'll start some cross-scanning after the pushover.
This F-111 is automatically holding 750 feet of ground clearance. See the hill a mile or so ahead in its path? Watch the pull-up. It's keeping altitude separation over the top. And now it's automatically pushing back down to maintain commanded clearance. We heard the crew talking about that pull-up a moment ago. They were reading out the displays on a piece of equipment that's new with the F-111. The terrain following radar, or TFR, gave the crew an early sight of that hill, a typical function of most radars. But then it did more. It worked out a vector equation. It considered their rate of approach to the hill's face, their angle of attack, their requested clearance, the time needed to execute the maneuver. It told them when they had that clearance, then pushed them over and leveled them off. This is the AN/APQ-110 TFR. Its foremost job is to sight and compute the vertical path of the F-111 in high-speed, low-level night penetration flights below hostile radar screens. That's tight work. Only the critical view of radar, the immediate steering command outputs of a computer, can be relied upon for flight control in this kind of mission performance. These functions are served by redundant circuitry in the set, a fail-safe feature, and a choice of modes for cross-checking the vertical scan of TF with the horizontal scan of situation. In addition, the set must be cross-fed by reliable inputs from the inertial platform, pitch attitude, the CADC true airspeed and angle of attack, and the radar altimeter giving absolute altitude and altitude rate of change information. The TFR relates these cross feeds to its own parameters, using them to measure any difference between where it is going, and where it must be at any point in its vector. To make up any differences, it will command the aircraft to climb or dive. When the AC can't see anything else, he wants to see those commands. The instrument coupler can put them right there on the ADI or LCOS, moving a pitch steering bar telling him to go up or down, or telling him he's holding his requested margin of ground clearance. Not only must the TFR see, analyze, command, but it must offer automated control of vertical steering too. Thus, its own commands may be engaged into the pitch damper by selecting Auto TF. The flight controls are now part of the computer. Pitch steering is automatic. Terrain following radar has 3 optional channels of sight. Of these, its primary view is along a narrow 8-degree beam, driven in a vertical scan pattern projected dead ahead. It scans 8 degrees above the aircraft center line and 32 degrees below this line. This is the TF mode. It is roll stabilized by the attack radar. It is drift stabilized by the inertial navigation platform. The TF mode is the most important of 3 offered by the TFR set. It alone is computerized. Its returns are basic to the requirements of computed terrain following flight. For terrain avoidance, the pilot may use the situation mode for a 60-degree view of what lies ahead, at his own altitude or above. Pitch, roll, and drift stabilized. This wider scan to the right and left of flight path is often used with the TF mode, offering a wider view of higher terrain along the flight path. The third view, in ground mapping mode, having the same stabilization as situation scanning, is of the ground surface beneath and ahead of the aircraft. Its scan may be tilted downward through 15 degrees of arc from the aircraft's horizontal. A navigational aid, it's a backup for the attack radar. This crew is ready to begin the TFR controlled flight. We'll assume they've warmed up the set and have run a procedural check on input sources, which we'll see more of later. But what do they do now? This is the mode select panel. Note the redundant left and right channels. Each is identical. The AC is going to switch each of them into TF mode. The first channel he turned on is now active. It will begin working its antenna, sending information to the computer. The second channel there on the left automatically goes into electrical standby. Should anything happen to the one on the right, which would be indicated by a fail light, the one on the left will be energized. The function of TF scanning and computing will not be interrupted. His procedure check gave him 2 good channels. He knows that the one on the right is sweeping its antenna vertically. It's seeing part of the terrain elevation ahead. Its returns are feeding into the computer. The computer is translating this sighted information into a statement which will reflect the influence of all the factors of the flight's geometry in relation to what its radar is seeing. It's ready to make this statement visible on the E-scope of the indicator panel. This indicator will show more than one kind of picture. Only the E-scope is compatible with the computer outputs concerning TF flight. This scope not only shows terrain returns, but it shows a constant expression of the computed flight vector reference as well. That's called the command reference line. The AC will be thinking about that reference line as he follows through with the 2 remaining and obviously very important inputs which he has control over. He goes back to his mode panel with a concern now for the 2 knobs there on the bottom right. Ride, clearance. He'll select a clearance setting first. The TFR computer now compares this clearance with the altitude information it is receiving from its own ground returns and from the radar altimeter. If the aircraft is higher than the requested clearance, the computer will generate a corrective dive command. If the aircraft is too low, the computer will order a climb to meet the higher altitude request. Clearance selections may be optionally changed in flight. Now the second of those knobs on the lower right of the mode select panel, the ride selection. Soft, medium, hard. This offers the commander an optional control of the gravity forces he'll experience in TF flight. A soft ride control, which the AC is now engaging, advances the pull-up command of the computer to an early start point, fairly far out in the approach track. Once clearance of the obstacles made, the soft ride's pushover command is given. It's relatively gentle. Its limit is 3/4 of a G indicated. Thus, as the TF is asking for a certain altitude lift, the ride control is calling for it early enough to smooth the action, reducing the angle and rate of pull-up, or G-force, and later, reducing the angle and rate of descent. The influence of the hard ride control is less tolerant. It lets the aircraft go into a minimum range from the target or sighted obstacle before the pull-up is received. Its programmed pushover begins quickly after clearance of the obstacle. This force may be as much as 0G indicated, and of course the medium ride control splits the difference as an influential input. It may produce a pushover of 1/2 G indicated. The maximum pull-up force in any of the 3 ride selections is 3 Gs as displayed on the G meter. We've been in terrain following flight for several minutes now. We've seen what the AC's inputs do to influence the programming of a true flight vector, which is the TFR computer's product. The AC now turns his attention to that vector or command line presented in the center of the E-scope. Now, we're used to looking at circular or pie-shaped pictures on radar scopes, pictures that show us plan views of things beneath us pretty much as they really are. Not so with the E-scope, for the presentation area of this display is rectangular. Not only that, but its picture is quite different from what its radar is actually seeing. The information in this rectangle is derived from an accurate but distorted profile view of the next 10 miles of course range we'll fly. While it's true the radar has our view dead ahead, the computer is using the information from that beam projection to give us a profile picture on the E-scope. The command line serves as a constant in that display. Actually, it's down there below us. It represents our requested clearance. We've separated it from our aircraft center line by whatever clearance factor we've asked for. That's all it is, a reference line flying along with us. But how did it become a double curved line on the E-scope? The upper and lower edges of the TF radar scan pattern represent the upper and lower edges of the rectangle of our E-scope. Repositioning these lines causes linear distortions within the picture field lying between them. Thus, our own relative position, at first a dot, was stretched out to form the left edge of the rectangle, and the leading edge of the command reference line was curved downward. That's the first part of the curve. The upper portion of the curve was graphically created by introducing influences of ride control selection. In flight, as the true airspeed is increased, this upper curved portion will flatten out slightly. As the true airspeed is reduced, the curve will become more upright. Similarly, the character of the leading edge of the curve will change as higher or lower clearance requests are made. Since we're most interested in what is closest to our aircraft in this display, it has been provided that beginning with the leading edge, the greatest part of the command reference line's length will represent the first 3 miles of our projected flight vector. The range scale has been reproportioned to conform with this nonlinear display. The returns from the terrain, that part of it which may be seen by the 40-degree vertical sweep of the TF antenna, enter our E-scope from the right at the 10-mile range mark. These will not affect the TF computation till they're within the 6-mile range. The TF computer only considers forward video from 1,000 to 36,000 feet. As they trace under the command reference line, their distance from us may be read on the range scale. An obstacle ahead of us standing above our clearance altitude will create a terrain video peak on our scope. Not only will we see its significant size, but if it's high enough to block radar beam projection, a shadow or void in the terrain video line will be created behind this peak. The computer does not tell us how high it is, but merely that it is higher than our clearance altitude. The approaching obstacle in our path suggests that it would penetrate the command or clearance line at about the 3-mile mark on our scale. This is all the computer needs to know to begin computing an appropriate pull-up command. When will the AC get that command? Well, that depends upon what he's asked the computer to consider. Right now, he's asking for 750 feet of clearance, which has moved the foot of the command reference line to the right for an earlier interception with the terrain video. However, he's also chosen the hard ride control. This has moved the top of the command reference line to the left, which means the terrain will intersect with it when we've moved in to a minimum distance from the obstacle. Had he chosen a medium ride control, a less severe pitch maneuver would result. Note the curve is in a less upright position for an advanced interception with the terrain. The soft ride advances this interception still further, and the command pull-up is witnessed relatively distant from the obstacle. With the hard ride selection, we'll get our clearance, but we won't get the command to pull up for it till we're well in. The obstacle is about 2.5 miles out in our flight path. The computer, measuring the contrasting requests of hard but late pull-up, will give the pull-up command early enough that our aircraft's reaction to its force will be compensated for. The AC does not read any displayed commands on the E-scope, only a picture of what's causing them. For visual pitch steering directions, he must turn to the ADI, which receives these computed commands through the instrument system's coupler. He'll choose one of the 5 modes on the ISC which are compatible with TF operation: TACAN, Course Select Nav, Nav, Manual Course, or Manual Heading. Then he must turn the pitch steering switch to the TF position. The pitch steering bar on the ADI is now receiving corrective flight outputs from the TF computer. If he's got the ADI operating, he may get the same pitch steering bar movement on the LCOS simply by turning this panel's control to any operative mode. These displays are merely practical expressions of the computer's equation in working a flight vector. The AC may make still further use of these commands by directing them to the pitch damper. This pitch damper normally is engaged during flight. Thus, to feed it those TF vertical steering commands we were getting on the ADI and LCOS, the auto TF switch is moved to the upward position. Vertical flight control is now automatic. The AC continually monitors this operation to assure that the controlled movement is following the pitch bar for corrective flight. If it is not, he must turn the auto TF switch off again to regain manual control, or depress the override paddle switch on the stick during any re-establishing maneuver. There's one function of TF which will allow us to begin a TF maneuver considerably above the computable terrain following vector envelope: the TF descent, sometimes called the blind letdown. The AC may begin this maneuver at any altitude below 38,000 feet. But we'll say that we're beginning ours at 8,000 feet. Now, the radar altimeter has a functional tracking limit of 5,000 feet. Up here, it won't read. It's not giving the TFR set comparative altitude information. We might surmise that the set simply will not function. And this would be true if it were not for the bypass mode of the radar altimeter, which the AC will engage at this excessive altitude before engaging the TF mode of the TFR set. In bypassing his radar altimeter, he's allowing a pseudo or substitute altitude value to feed into the TFR computer. This pseudo input will be compared with the requested clearance altitude, we'll say 1,000 feet. And the pitch damper will get a descent command through the auto TF. As long as we're above 5,000 feet, the pseudo altitude input will confirm the descent command computation. But when the aircraft drops through the 5,000 foot mark, the radar altimeter kicks in. Now, we're in normal TFR controlled flight again. The 8-degree TF radar beam discerns target positions along the ground track within 0.82 degrees of accuracy. But the computer receives no information about obstacles outside of that 8-degree beam spread to the right and left of the radar's track. All the computer knows is that if the aircraft turns, it will swing its radar scan track with it. Aware of this, the AC will never exceed 10 degrees of bank while relying on the E-scope picture alone. Lead into turn TFRs can bank 30 degrees. If he's going to alter his lateral flight path, he should use the situation mode of the TFR set. This will present him with lateral search information at his own altitude or above. He turns the reserve channel to situation, then chooses a range setting, 5, 10, or 15 miles on the indicator panel, for a situation scan display. Accordingly, he'll get a view of 30 degrees azimuth on both the left and right side of his flight path within the selected range. Situation mode contributes no inputs to the TF computer. The crew will use its display as a cross-check to see if a general terrain avoidance maneuver might hold more tactical advantages than would flying directly over an obstacle. The TF radar will receive returns from most all terrain compositions. Yet some ground or water surfaces allow the radar's beam to slide or dissipate in an obtuse angle of deflection away from the aircraft. Sand, wheat fields, dry lakes, or the sea may cause this. An absence of returns detected within a 1,000-foot band of terrain lying between 3,500 feet and 4,500 feet ahead of the aircraft will activate an override feature of the radar altimeter. Looking straight down, the radar altimeter provides altitude rate of change information to the computer until the aircraft has cleared the field of non-responding surface. The override function of the radar altimeter cuts out as the TFR receives returns from general terrain compositions. Now, prior to takeoff and TF-controlled flight, a procedural check of the TFR set is conducted by the crew. They know a malfunction of an input to the TFR computer will fail the set, thus automatically generating a fail-safe 3G pull-up. Also, a failure to maintain 68% of the requested altitude clearance will automatically interrupt the flight vector with a 3G pull-up maneuver.
Left and right channels of the TF in standby. Warm up and fail lights are out. Press the test of the TFR fail lights. Good. Radar altimeter on. I've checked both channels in TF. Situation and ground map. Looks good. We're ready for takeoff now. Be sure both channels are back in standby. Raj. Radar altimeter in bypass. Setting left channel to TF. Self-test. Looking good. Setting clearance at 1,000 feet. Radar altimeter indexer set at 800 feet. LCOS is on. Pitch steering switch to TF. Got good clearance shown on the E-scope. Video and memory adjusted okay. I'm putting it in auto TF. It's taking us down to 1,000 feet. Pitch steering's good. There's 1,000. I'll reset for 500 clearance. We're passing through 680 feet. Radar altimeter low light on. There's 500. We're leveling. Reset our clearance for 1,000 feet. Check the TF and radar altimeter warning lights. Reset. Lights okay. 3G pull-up. We're pulling above 680. Warning and fail lights out. So much for the left channel. Now let's try the right one. They're both good. I'll check for changeover. Both channels in TF. Now the active channel to standby. It's giving a light. Changeover's okay. Same for the standby channel. E-scope is good in both channels. Self-test working. We're about ready to go TF. First, let's do the drift checks. No crosshair drift in ground vel. Ground track and true heading compare okay. Wind speed okay. Ground speed and true airspeed check. Okay, we're ready for TF.